Hi, my name is Logan Grove, and this is my research presentation on quantum-enhanced decision-making, how quantum mechanics can solve problems that are classically impossible to solve. In information theory, information is represented in units called bits, and these are ones and zeros. They are binary digits, and they can represent one of two values, in this case, ones and zeros. In quantum mechanics, we've enhanced on this theory and created something called a qubit, or quantum bit. And this is in a two-level quantum system, and it has some major advantages over classical bits. They're able to represent information in new ways, via properties of quantum mechanics like entanglement and superposition, which give them large advantages when compared to classical bits. While unobserved, qubits exist in something called a superposition, which is sort of a combined state limbo of their two possible states, in this case a 1 and a 0. And it is impossible to predict what state will be measured when the measurement actually takes place. And this is because quantum mechanics is inherently probabilistic. For example, a qubit could have a 75% chance of being measured up and a 25% chance of being measured in the down state, but it's impossible to determine which of these two states will actually be measured. And this allows for the retention of more information because any state can be represented by any combination of 1 and 0. Another inherently quantum property of qubits is something called entanglement, and this allows physicists to link particles over arbitrary distances. When two particles are entangled, it means that when one particle is measured, the other particle will always have the opposite state. For example, if Alice measures her particle as spin down, Bob will always measure his entangled particle as spin up, or vice versa. And this sparked something known as the EPR paradox, standing for the names of the three physicists who coined it, Einstein, Podolsky, and Rosen, and they were afraid that entanglement violated the theory of general relativity. And they thought that the particles were communicating, in a sense that particle 1 was sending a message to particle 2 to tell the second particle what state it had been measured in order for particle 2 to correlate its result. The ideas behind the EPR paradox were accepted by the scientific community at large, and in fact it went unchallenged for about 30 years. Einstein died believing that the ideas behind this thought experiment were actually true, and that there were some things inherently unknowable about the physical universe. That all changed in 1964 when a physicist named John Stuart Bell made a breakthrough. He developed a set of equations that could never be proven false by classical physics. Shown here on the right is one such version. It pits the statistical nature of the physical universe against what our predictions of quantum mechanics would be according to the communication theory supported by the EPR paradox, and shows that one of them has to be false. This version is the LSVP theory, shown in the top left of the board. And what these did, they essentially tested if the particles were communicating, and they could only be violated by quantum mechanics. And a violation would mean that quantum mechanics was true. Here is arguably the most famous version of the Bell inequality. It reads as the mean value of Qs plus the mean value of Rs plus the mean value of Rt minus the mean value of Qt is always less than or equal to 2. Q and R are properties of one qubit, and S and T are a property of another. And each of these properties evaluates to only positive or negative 1. This equation should never resolve to be greater than 2, and any such violation of this is known as a violation of the Bell inequality and can only be achieved through quantum mechanics. There are many different versions of this inequality. The version pictured here is known as the CHSH version. The version pictured on the previous slide was the LSVP version, but they are all similar and they all prove the same thing. Here it's easy to see that the equation can only evaluate to positive or negative 2, given all of the possible iterations of Q, R, S, and T equaling either positive or negative 1. This is only classical, however. If Q, R, S, and T are replaced by possible values for qubits, this equation approaches 2.82, which obviously is greater than 2 and is known as a violation of the Bell inequality. John Stuart Bell's seminal paper in 1964 is key to this research. Bell developed a set of inequalities that could only be violated by quantum mechanics, and it proved that entangled particles do not communicate or share information. Peronio et al. In 2003 built upon this idea and showed that communication is enough to force a Bell inequality violation, and if used correctly, the results would seem like communication to any untrained viewer. This is important because it realizes the idea that quantum mechanics can actually be used for partial communication. G et al. In 2019 was one of the first to formulate a game based on the Bell inequality, where it separated two players and coordinated their action through quantum pairs. And it showed that an advantage was akin to a Bell inequality violation, but it was impossible to predict how much advantage they would gain. This was again important because it built upon the idea that quantum mechanics could be used for real-world advantages in communication. Finally, in 2020, Lin et al. Developed a game that showed that Bell inequalities can give real-world advantages, but it only applies to a specific set of cases. In particular, they pitted the game Blackjack against the Bell inequalities and showed that when there are a few number of cards in the deck, two players, Alice and Bob, working together can actually gain an advantage when compared to classical non-communicating pairs. You can see here in this bottom graph that their advantage actually drastically increases as the number of cards in the deck decreases. Shown here on the right is typical game setups with Alice and Bob working together to communicate and pair their actions. Taking these previous works together, we can try to develop a classical game that will test the Bell inequalities. In essence, this game will be impossible to win classically, and winning through quantum means would provide an advantage when compared to real world, and provides a blueprint for applications to Bell inequality in regards to communication and information transfer. Here is one such version of these tailor-made casino games. Say Alice and Bob enter a casino. They're immediately separated from one another and can't communicate on their actions. The casino will flip a fair coin for each of them that will land on either heads or tails. From there, they'll each have to choose to press one of two buttons, a red or a green button. And the rules of this game are as follows. Bob and Alice are trying to win as much money as possible, as is usual in a casino. They will press different colors if they decide to play, and if they press the same colors, they will skip the round. They should decide to play if they think that they have a winning combination, which is when both of them have flipped heads. In this case, they will win $1. But in any of the other three scenarios, tails heads, heads tails, or tails tails, they will lose $1. This would be the best choice for them to skip, in which case they don't win or lose money. A flowchart of the game is illustrated here. A coin is flipped, Bob and Alice see the results, and then they decide to press a button. From there, they can decide to play or skip, but remember, they can't communicate with one another. If they decide to play, having pressed different color buttons, they will either win or lose $1, and then a new round will start and a coin will be reflipped. However, if Bob and Alice choose to skip by pressing the same colors, a new coin will be flipped and no money will be won or lost. Let me try to illustrate to you that this game is impossible to win classically. Say Alice flips heads and presses a red button. Bob, if he flips tails, would also press red because he wants to cancel play and avoid this losing heads-tails combination. But say now Bob has flipped tails and Alice also flips tails. Obviously, again, she would press red because she wants to avoid the losing tails-tails combination. Now let's say Alice has flipped tails and Bob flips heads. Again, Bob will press red because he wants to avoid the losing tails-heads combination that's made by this scenario. However, this leaves the winning heads-heads combination classically frustrated. Any deterministic classical strategy will be faced by this frustration. This game is impossible to win classically, and it's shown via Aristotelian transitivity. Classically, Bob and Alice's profit is always less than 0. 3 out of 4 times they lose money. However, this situation is a Bell inequality, in which they can generate a quantum profit, which actually approaches about 12 cents per round. If they continue playing, Bob and Alice can make some serious money. What was just illustrated is known as the classical casino game. However, it also has a quantum counterpart. This game has the exact same setup as the classical game, except for that Bob and Alice each have boxes containing entangled singlets. These boxes measure a specific property based on a coin result. Bob and Alice will decide to measure one of two properties based on which button they choose to pick. The result of that measurement is the output, and it tells Bob and Alice the best game choice. This is a Bell inequality violation, and it helps them work towards that 12 cents per round profit. This beats the classical strategy, which on average always lost money. Now again, Bob and Alice won't make profit every round, but on average they'll earn about 12 cents. There are some major applications for Bell inequalities here, and it's a useful tool for partial communication. It has to be a suggestion of binary states, which are yes or no answers. These can be things such as stock market fluctuations or trade confirmations that Alice and Bob are working to get together to secure maximum profit. However, the answer must be rooted in probability, just like the classical casino game. Otherwise, the scenario isn't applicable. The goal of this research is to identify scenarios where the Bell experiments and the application of qubits can be made into real applications for partial communication. We want to see how this can impact life in the future for real applications of information suggestion. Our hypothesis is that significant effects of these properties and Bell experiments can be applied for real information suggestion. So far in this project, we've written classical versions of this casino game in Python. There are single, double, and automated player games, all of which have different methods but very similar results. In the single player game, the user can pick from one of four computer protocols that dictate the computer's choices as it plays. They start with a set amount of money and continue play until that amount reaches zero. At the end, a graph of their money per turn is output as they play. The automated game is very similar, and it allows the user to pick from one of the four protocols established in the previous version. However, the user sets protocols for both Alice and Bob. The game will run a specified number of times and record the max profit that Alice and Bob reach. And it graphs the frequency of each of these max profits with a best fit line that reveals some very interesting results. We're also working on coding the quantum casino game in something called QTIP, which stands for Quantum Toolbox in Python. This is used to simulate quantum systems, and in particular will help us work on simulating the 2-qubit system that Alice and Bob use in the quantum casino game. The results of these experiments were very interesting. In fact, the automated game revealed results related to the secretary problem in optimal stopping. Shown here in the upper right is the output from one of these simulations, which shows that the majority of these trials never breached their starting amount of money. On the bottom, you can see that Alice and Bob lost money on almost every round. Our expected results are that the quantum casino game will reveal scenarios in where Bob and Alice win more often than not when compared to the classical game, and this should give us the basic format for real-world scenarios. Shown here is a possible graph. In this case, Alice and Bob communicated classically, but as Peronio et al. Showed, communication is akin to a violated Bell inequality, and you can see the general upwards trend on the graph as opposed to the downwards one for the classical game. As I mentioned previously, the automated game revealed results related to something called the secretary problem in optimal stopping. 2/3 of the total tries never breached their starting $10 amount. And from there, the result exponentially decreased. Between 1/4 and 1/5 earned $11, and there is a decreasing chance of earning more and more money as the trials go on. This was run out of about 10,000 games, and it reveals the question of the best stopping point if the scores are hidden. Essentially, when should Alice and Bob quit without knowing how much money they have? For the quantum casino game, you'll still notice that there are some flat areas on the graph. However, there will never be a general negative slope, even though the slope in some areas may decrease. And this would be like if the partners could communicate. This would be used for identifying real-world scenarios to implement this partial communication strategy. If successful, this research would allow for partial communication where classical information transfer is impossible. This would also occur over arbitrary distances, which has its obvious advantages. It also doesn't violate relativity because each partner must wait for the other to enter their result, and therefore it fits within our classical description of the world. It also allows us a better understanding of the Bell inequalities, a theory which was established nearly 60 years ago, but we're still beginning to understand the applications of today. In conclusion, our research is aiming to identify real scenarios where the Bell inequalities are used for partial information transfer, and it allows for computer simulation of real quantum events that have an impact on the physical world. When completed, it'll allow for partial quantum communication over arbitrary distances where classical communication is impossible. And it's also the application of a theory created in 1964, which for all intents and purposes has laid dormant in terms of real-world applications. It's simply a mathematical construct that helps us better define our meaning of reality, but hasn't much contributed to it. In the future, I would like to deepen my understanding of the topic as well as code the quantum casino game, which will allow us to get the basic format for real-world advantages and find where this can actually be applied for partial communication. I would like to thank my mentor, Dr. Rodrigo Cortines, who's given me a lot of guidance through this project and has helped me understand a lot of the background material. I would also like to thank my teacher, Miss Jillian Ronaldo, for her support throughout the class, as well as my family and science research peers. Here are my references. Thank you. Any questions?